I'm a Christian. I'm a LXD developer and also a kernel developer working for Canonical. This is Stephane, who's the project leader for LXD and also for Lexi. He's also working for Canonical, and yeah, we're the two guys who are giving the workshop today. So cool that you all came, and we're excited. Yes.
Just looking around, we've got 1, 2, 3 at least seats with tables, table space here. So if you're probably gonna have to type stuff during the lab part, so it might make sense for some of the people to move to be a bit more comfortable.
So we're LXD. As some of you might know, we're focused on system containers, actually, and not on application containers. So the difference is to just running a single application inside of a container, we boot a whole init system, and we don't care what init system, OpenRC, systemd, it all works at this point. They're actually the oldest types of containers, and we're not the one who invented them. We're not the ones who invented containers. They have a long, rich history. They trace back basically to BSD jails. Then there was an implementation called Linux vServer. Then there was Solaris zones, and the OpenVZ guys did an amazing amount of work in the kernel and for containers in general. And then there was Lexi and LXD. So there is a long tradition of containers, and a bunch of people worked on them. They behave like standalone systems, so there is no need for specialized software or for custom images. So you can basically just debootstrap any kind, or debootstrap. You can just create a rootfs for your favorite distribution, give it to LXD essentially, and it will just boot it. No modifications, nothing needed. It was a long way to get there, but it is actually possible. And it's somewhat not very much different from virtual machines in that respect. And obviously, since they're containers, there is no virtualization overhead that you get with virtual machines. So there is no hardware virtualization or anything happening. Yes, what is LXD? We like to refer to it as a container manager, or as it's put here, a container Leiterweiser, but container manager is actually nicer. It's a daemon that runs containers. It's pretty simple. It has a clean command line interface and a simple REST API, and which Stephane mostly designed, and a very clear terminology. So it tries to be it's easy to understand what is actually happening with those comments, or at least we aim for that. It's fast, something I said before. There is no virtualization overhead, and it's almost as fast as bare metal. You can read papers about this if you want. And it's secure. It means it's safe by default, and especially means that we try to make use of every user space and kernel security feature out there. So for example, we by default run unprivileged containers, meaning we isolate UIDs and GIDs inside of the container from UIDs and GIDs on the host. So we separate the privileges that are used inside of the container from the privileges that are used on the host. That is the whole shtick of LXD, or one of its main. It's scalable in the sense that you start off from a single container that you use to develop stuff on your local laptop, or you spawn thousands of containers per node in a data center because LXD itself is distributed. It isn't, and this is something we try to make very clear, another virtualization technology. We try to offer an experience that is very close to that of a virtual machine, but we don't try to be a virtual machine. We aren't virtual machines. So you always get real access to the underlying hardware and real native performance. It's not a fork of Lexi. People usually confuse this. Lexi is a low-level API, essentially written in C, that is used to manage containers, and LXD is calling into Lexi to run containers. The idea basically being that this low-level C API allows you to interact with the kernel in a very native, in a very native way, because the kernel itself is also written in C, and you don't get all of the problems that you have from higher-level languages like Go. And it's not another application container manager. We have no beef with Docker. We try not to compete with Docker. We only care about full system containers, and yeah, we don't care about what runs inside of the container. There's no special casing for any kind of application whatsoever. So this is sort of the layout that you would expect when you run LXD. You have multiple hosts, for example, in a data center or distributed across the world, whatever you want. They all run different versions of the Linux kernel. They could potentially run different versions of the Linux kernel LXD itself, the API that is used to run containers, is backwards compatible until 2.632. So you could have one kernel 2.632 and the other one 418. We have restrictions, but technically you could do it. On top of it, it's LXD. LXD is responsible for running the container, and then you have LXD, and LXD exposes a REST API that you can also expose to the internet, for example. And then you can use whatever client tool you want to communicate with the REST API. You can have a Nova Compute LXD plugin for OpenStack. You can use our own command line tool to manage containers, or you can have your own client script because we expose a specific API. Yes, and I'm handing over to Stephane, but we need to switch microphones. Okay.
I'm good. All right. So the different components of LXD itself. LXD is a container manager, so obviously we've got containers as the main primitive in the API. Those containers are created from images, so all LXD daemons act as a image server. You can publish your own images locally. You can make them public, at which point someone who's not even authenticated to the API can pull those from your machine. We've rerun public image servers as well with images for most Linux distributions. And that's what you usually will use to then create your containers from that. As Christian said, we're running system containers. So unlike what you get with the application containers like Docker, where you'll get a set of layers to get you an image for a specific application you want to run. For LXD, what you get are pristine, sometimes officially blessed images from the Linux distribution. And then you install packages and you manage it exactly as you would a virtual machine. The other components we've got are profiles. Profiles let you effectively combine configuration data and then create as many containers as you want from that, so that you don't need to copy paste the same configuration over and over again. It also has a nice advantage that if you modify a profile, everything is modified live. So one of the examples that you're going to go through in the lab part is putting resource limits, for example, on a profile, and any container that's already running will now see its CPU or memory or whatever shrink or expand based on what you put in that particular profile. We've got, we had those components already from the initial LXD release back, 4 years ago or whatever now. We've then added some big pieces of API since. One of those was network management, so that lets you create network bridges, including things like VXLAN tunneling, fine configuration of IPv4, IPv6, some amount of firewalling that you can then use with your containers. With the piece after that was managing storage. So at the beginning of LXD, we only really supported a bunch of different storage backends, but you had to choose one, and that was it for everything. That changed year and a half to 2 years back now, where we can have many storage pools that can each be backed by one of our storage drivers. What we support there right now is ZFS is preferred. Otherwise, you can do BurFS, or you can do LVM, or you can do Ceph, or you can do plain old directory storage. And you can create as many storage pools as you want using any of those backends. And then on top of storage pools, you can create volumes. Some will be created for you, like containers obviously get their own volume. Images get their own volume. But you can also create custom storage volumes that you can then attach to one or multiple containers. So you can share data between them that way, or you can have, say, a storage pool that's on SSD, on a very fast SSD, when the rest of your storage is on slow hard disks. And you can then allocate a volume for your database on the SSD storage pool and attach that to your container so that it gets fast storage for some specific data. And the feature we added actually earlier this year in LXD 3.0 is clustering. With that, you can very easily have multiple LXD instances be connected to each other and effectively act as one big LXD. So API-wise, you don't even need to be aware that it's a cluster. You can act exactly like if it was a single instance, but it's going to do round-robin balancing for your containers between the different machines. It's going to do automatic image copies between them. So that's pretty neat if you're running an environment where you've got a number of compute machines and you don't really care about where things are, but you want to easily give people access to that so they can spawn whatever they want. Now, bit of details like and I covered a whole bunch of that already, but so on the clustering piece that we added this year, the nice thing with LXD clustering is that unlike other sessions, it doesn't need anything external. You don't need a separate database, you don't need a separate daemon or whatever. Like LXD comes with it built in, you can turn it on whenever you want. No external dependency, no nothing, it just works. The database itself is replicated on up to 3 nodes by default. So it ends up being a cluster database that's consistent on your entire cluster. If one of those goes down, things still work. You can reboot compute nodes, and those containers will be offline during the reboot, but that's pretty much the extent of it. And like as far as scalability, we're still working on a number because like we were doing tests of LXD at scale in the past, but we were considering 500, 1,000 containers to be a lot because we were looking at a single machine. Now we're looking at what happens when you run 10 to 20,000 containers as part of a cluster. So it does scale. We've been improving things quite a bit recently. My test cluster is happily running 2,000 containers, and even listing, even complex queries, like say you want to get the detailed IP configuration and IP state of every single container in the cluster, which actually involves having to attach to every single one of them and pull that data out of the kernel, which is kind of slow. That takes, I think we were looking at something like we can do 100 containers per second or something like that for those kind of queries. So it's not quite what we want, but it's getting close.
Faster.
Yeah, it's going to get faster. We've got kernel work coming up that's going to make some of that stuff massively faster. All right. So I think we have done mostly with talking for a little bit. So we're going to go and do demos. Christian's going to come and do the first few. So I just need to switch things a bit. So we're going to get to see this. And we get to see that. And that you should be good to go.
So performing demos on someone else's computer, this is always challenging. It's going to be fun. You can laugh at me. Exactly. So the first thing we're going to do is install LXD, and we're going to use the snap for this, in this case, if I ever make it to the right window. OK, so we're going to use the snap for this, as I said. Snap install n. It's going to take a couple of seconds, but yeah, it's going to pull the LXD snap and it's going to install it. Oh, by the way, while we're at it, it's like how many times have actually used, how many people have actually used LXD and LXD here? Ah, cool, a few. So the first thing you need to do is call LXD init, which basically initializes LXD. So there's a bunch of stuff you need to do. For example, you will not have a storage pool, meaning you cannot just create a container because you have no storage backend defined, right? So we don't want clustering in this case. We definitely want a new storage pool because we need something where we create our containers on. We leave the name at default because it's just easy. And we're going to go with ZFS for the beginning. But you see you can choose between Btrfs, Ceph, directory, LVM, and ZFS. So yes, we don't want to use an existing block device in this case. So we're just going to use a loopbacked file system for this. And we're going to leave it at 15 gigabyte. We don't want to connect to a MAS server. We want to create a network bridge, yes, called LXD bridge 0. And yes, it's going to be auto for the IPv4 address and for the IPv6 address. We would like to be available over the network. No, not now. Stale cached images updated automatically. Yes, we definitely want this. So you always get the newest version of the distro. And if you wanted to, you could print out a config, like the config that has just been generated internally. You could print it out so that it can use as. Oh, we can say yes, then let's do it. So you see, this is the configuration essentially. that you use for this LXD instance. If you wanted, you could save it to a file and then send it to someone so that they can initialize their LXD instance in exactly the same way. So now LXD is basically ready for work. We can launch a container. Ubuntu, let's in this case, and let's say 18.04. Let's call it C1. It should be pretty fast. The first one will download the image, and it will create a container from it. And it will use all of the advanced features that the file system supports. So CFS, for example, supports instantaneous snapshots and so on. So the first time it's going to be slow because it sets up the pool and the volume, and the second time it should be pretty fast. So if we like, for example, say create a second container.
Yeah, where are you downloading the image from? Is there a repository that you're downloading it from?
Stephane?
Yeah, so there is. We've got, it's actually going to be covered in the lab, but we do have, by default, LXD comes with 3 endpoints for images. 2 of them are official Ubuntu images. The third one is called images and is the community image server that we use for both LXD and for LXD. And we've got images for most distros in there that we update daily.
Stephane, there is another question.
Do you have to be root when you're creating the instance in it?
So you don't. Whoever is in the LXD group can talk to the LXD daemon. So you can install it with, usually installing it, you'll need to be root. After that, if you're in the group, you can talk to it and configure it. So even LXD init can be run as a normal user because everything happens over the REST API. By default, because we told it not to connect to, well, not to listen to the network, in which case it only listens on a local Unix socket. And whoever has access to the socket can control LXD. For demo purposes, we just do things as root. It's easier. But yes, in the lab, it's going to be as an unprivileged user, effectively.
So if you want to spawn, or if you want to execute a command inside of a container, the exec command is what you want. So LXD exec container name and that whatever you want to execute. In this case, I want to execute password Ubuntu. Do it, then we give it a new password, which is very secret and you can see very long. And then one of the nice features is we said we want to be like extremely close to what a virtual machine is actually doing. So what we allow you to do is you can log into the console, actually. So let's see console, C1. And then you see you're literally logging into the container now. Let's see if the password works. It works. Yes. So you can really log into one of the TTYs. You could even configure it. There is low-level ways available to, for example, tell LXD to allocate, I don't know, 200 TTYs if you wanted to. And systemd will happily run gettys on all of these TTYs, so you could log into it from everywhere. This also works remotely.
Will this all work for ARMv8 also? For example, maybe not natively, but I'm thinking, hosting LXD in Android, running ARMv8, and maybe you first have to be on a ARMv8 Linux workstation first. But
yeah.
Yeah, so I've not tried on Android itself, but we do build and run on x86-64, i386, ARMv7 HF, ARM-HF, so yeah, ARMv7 hardload, ARMv8. We run on S390X, PPC64, PPC32 Big Endian, and PPC64, and S390, PPC64EL. Yeah, so we run on most, like pretty much anything that the Go compiler supports, we support, and we even support some of the GCC Go only platforms. I think someone tried MIPS, but not can't remember how successful that was.
So low-level LXD, the C API that is underlying all of this, basically, it runs on everything. So it runs on MIPS. People run it on WRT, is it?
Yeah,
I think
that's what I was gonna say. I think someone managed to get LXD running on an ARMv8
they
OpenWRT.
even sent a seccomp patch, yeah.
Yeah.
Exactly, and like the Google guys on their Chromebooks, they use LXD.
That is a good point. So yeah, if you anyone running a modern Chromebook, you've got that Linux app thing, and that's LXD actually. So and that runs on both x86 and ARM64 Chromebooks.
Right. You can also we're still in the container at the console, but you can Control D, but you're obviously still locked into the console. But now we need to get out of it. Oh, how is it?
Control A Q.
Oh yeah, because
you're in nested tmuxes.
Yeah, that is fun.
Normally it's Control A Q.
Yeah.
You've got a few. Do you need me to do it?
Yes. That's not tmux, is it?
It's screen plus tmux. Oops, sorry. There you go.
See?
Normally much easier than that.
Yes. Exactly. You could also, if you wanted to, for example, we have so LXD itself maintains a ring buffer, which you can query so that you can see, for example, because we boot an actual Linux distribution, right? And you obviously, this has started in the background when it created a container, but sometimes you realize you log in and you do ps-aux and you see systemd has just crapped itself in there. Systemd has just problems booting. And you want to know what exactly, if I'm cursing, I'm very sorry. You want to know why it happened. And so that's why we thought we implement a ring buffer in LXD that records. You can set the size automatically. It's I think 128K, and you can look at the ring buffer to see what actually happens. So this is what we can do. We can say LXD console show log for the container C1, and it should show you. Oh.
Or don't you have a C2 yet? I don't know. Oh, no, you don't have a C2 yet. Oh, fine, do C1. The thing is that C1,
No,
because you used it... Oh, you've got a C2?
I got a C2 because
Okay, cool. Because C1, because you logged in, that got flushed. So that's why you want to look at C2
it's not
for
flushed,
the...
it's recorded, but you can see a bunch of stuff. But how
That's
how
nicer because you see the actual boot log of that one since you never logged in.
Can I just scroll up somehow?
No.
Okay. So, but you see...
Exactly,
no. No, don't. So exactly, you can see what's going on. That's pretty useful. And also, that's what Stephane said. If you log into the console and you start typing stuff and so on, it will go into the ring buffer as well. So the ring buffer, if you wanted to, for example, you could set it such that these ring buffer logs are always saved. But we designed the ring buffer in such a way per default that it is a ring buffer. It means it overwrites. It never goes over 128K because you know what happened in the initial implementations of libvirt. It's like basically you're spamming the whole disk with with the log, essentially. Because if there is something in there, for example, if I were to log into the container via the console and type in yes and just leave it running, I'm basically filling up the disk of the host. And this is not going to happen because the ring buffer is just wrapping around. Exactly. Exec I showed before. You can exec stuff inside of the container. You can get a shell if you don't care about actually being attached to the console. You just do LXD exec bash, and you can log back out. It's also pretty neat. It takes care to never truncate the output and so on. So even if you run commands that pipe a lot of output very brief into your window, LXD itself will take care that nothing gets lost. And you can also get information about the container itself. To query, for example, what IP addresses it has. You see the PID, you see what profiles it is attached to, if it is a ephemeral container that gets deleted when it's stopped, or if it's a persistent container. You also get information of all the resources, processes running in there, disk usage, root, CPU usage, memory usage, and so on, network usage. It's all right there. And you can create snapshots, obviously. This is something what people want usually. So I'm creating a snapshot of the container. I'm doing C1, and I'm removing, for example, RF. Let me remove, let's say Etsy, right? It's a good example inside of the container. I've removed this. Now let's see if I can still exec in the container. I have no name. Yeah, that's going to be a problem. So I can just restore from the snapshot and say restore C1, snap 0 in this case, right? And then if I'm going back in, things are all fine again. Yeah.
Was the container still running when you did that?
That depends on the back end.
Depends on the backend. In this case,
Yeah.
yes, it was.
So didn't it like freak out when it set wrong way?
No, it really.
Actually, I think restore restarts, snapshot doesn't. So the snapshot doesn't
Sure.
restart the container, the restore does. And snapshot, as I said, is depending on the backend, because if you're like on Ceph, LVM, or some of those,
They take
freezing
care of-
without
yeah.
potentially corrupting the file system, but without potentially having an inconsistent state of the file system when you do it, might be a problem. But with ButterFS, ZFS, and directory, it's not an actual problem.
ButterFS, CFS, and also LVM can be used while it is running, because LVM, for example, as far as I remember, also takes care of freezing the file system, but for example, Ceph RBD doesn't. So if you do an RBD snapshot on a file system that isn't frozen, you might end up with no data whatsoever in there. So yeah, this is file system specific. Yeah. How can I go down here, Stephane, on your laptop? Next slide. Next
No,
slide.
it's still here. There. Oh, yeah, just there. There you go.
Cheers. We also support stuff like resource limits and so on, meaning by that you can limit your memory and whatever it is you want to do. So let me see if I can manage to copy and paste on Stephane's laptop.
I can do it if you want.
Yeah, I think that's faster.
Okay, so resource limits. First thing first. So a bunch of you might know instance type names from like various public cloud. And for other convenience, we actually support those. So we've got, in this case, I can create a container. It's gonna, oops. I'm just gonna delete C2 real quick. I forgot that we already had one called that. That's fine. In which case, it's gonna apply the memory, the CPU and memory limit of what Amazon would call a T2 macro. So we can go and check that in the container.
Stephane, if I can suggest, put your command line at the top so it's easier for everyone to see.
Yeah, it's okay. We'll try and clear the screen more often. So yeah, CPU info, you only have a single CPU listed now, whereas the VM had 4, I believe. And memory, we're down to about a gig. So if we go see config show of the container itself and look for limits, there. We see that the container config now contains limits for that. We can just gonna create another container real quick. Just I'm using a CentOS 7 image. Okay, so in this case, we've not applied anything. We see 8 gigs of RAM, the whole 15 gigs of disk space, and we should see 4 CPUs. There we go. But we can change that. So let's apply a memory limit of 512. Let's apply a CPU limit of 1 CPU. And let's modify that root device and put a 1 gig quota on it. And okay, so we've done that. Now let's clear and do the memory. It's 5-ish, 500-ish. DF shows we're at about a gig, and CPU is we're down to 1. All of that happened live. The container didn't get restarted or anything while that was applied. It's just live modification of C groups and quotas.
So for every feature, yeah.
Alex has got a question.
Every feature that we can figure out a way to apply live, we apply live.
Yeah. So yeah, in this case, it's ZFS, so it's the ZFS quota has just been modified. For BurFS, we do it through queue groups, but then it's not visible, and also it's bypassable because queue groups. LVM, we do a block resize, so you can grow live, but shrink will require a container restart. Same thing with Ceph. So
X for
Yeah.
XFS and ButterFS.
yeah, so those are the ones we support for when on top of block devices. Yeah, so just XFS
exactly.
you can grow, and if you try to shrink, then no such luck.
So we allow growing and shrinking for XFS because they provide tools for that, obviously for ButterFS, but not for XFS because it just doesn't work.
Yeah. So and we do support the file systems that people want, but also if the file system doesn't support a feature, then we've got to deal with that. So that's for resources. Another thing that's interesting is we've got devices. Like you saw me override the property of the disk device, but more interesting devices would include things like GPUs. So that VM's got two rather bad, but slow and whatever, we don't really care, NVIDIA GPUs. Now, if I go into my container and I try to run the same command, that's not going to work so well because it's a clean Ubuntu container. Why would it know anything but NVIDIA? But we can set a property, which is NVIDIA runtime, which that one does require a restart, unfortunately. Which would then load an NVIDIA hook that's written by NVIDIA and will do automatic pass-through of things like the CUDA libraries and the tools and all that stuff. So you don't need to install a gig of stuff inside the container. Now, if I do NVIDIA SMI again, no devices have been found, but the tool is there now, so that's progress. But we should give it some GPUs. So let's add a device, call it GT731, because I've got two of those. It's a GPU, and let's use the first card, so it's going to be ID1 in this case. If I run NVIDIA SMI, we've got one GPU in there, yay. And now we can do the same thing with the second one if we want. And we've got two GPUs. We've got different ways of selecting GPUs. That's the simple give me the first and give me the second. We can also select by PCI ID. So we can actually say, I want this specific device, and we track down which one it is, and we pass it for you. And you can filter by product ID, vendor ID as well, if that's more convenient. The problem is that in this case, it's two of the same card. So product ID and vendor ID would just give you both. Doing ID-based was easier than me typing a long PCI address. Oopsie, I did one more control D than I meant. Yes, can you?
Sorry.
What if we have a custom PCI device and we want to enable support of being able to add that to the container? What do we have to expose to be able to do that?
So it depends. It really depends on the device. So for GPUs, we've got logic that does a track down. That's fine. We've got pretty good support for USB devices. Those are pretty easy, vendor ID, product ID, and we pass the dev bus entry for you, the dev bus USB entry for you. For most everything else, so if your driver gets you a bunch of Unix character device or Unix block devices, we've got a generic Unix-char and Unix-block device type that lets you pass any of those into the container. Yeah. So that tends to be the easiest way. We have some abstraction as well for things like InfiniBand. So people passing an InfiniBand device, we automatically do the figure out what the virtual function is if you've got SRIOV. Figure out what the IB device is for IP over IB, and then figure out the UVert, UVerbs, whatever, like all of those devices.
UMAD, whatever it is.
So we figure out the set of devices and we pass those for you.
RDMA, essentially.
Yeah. So like, effectively, for us, USB, GPU, and InfiniBand are convenience that we've put in place on top of our Unix char device pass-through. Because all of those, at the end of the day, they pass character devices inside the container.
Exactly. So, and you can also set UID and GID, for example. You can tell it which UID and GID the character devices or block devices inside of the container are supposed to be shown to, and also you can set the mode and so on. Yeah.
Yeah. Speaking of, there's one more question there.
This sounds like you can't assign an arbitrary unknown device to a container, is that right?
Right. I mean, because it wouldn't work anyway, frankly. For USB devices, we can pass you something that a driver doesn't even know about, because then you can use libUSB to drive it. That's fine. For arbitrary PCI devices, the only way you can drive them is with a kernel driver, and we're still those are containers, so it's a shared kernel. So you should be loading the kernel driver on the host and then pass the resulting device nodes into the container. The container itself cannot load kernel modules and shouldn't do PCI access directly.
But
so.
you can, for example, tell LXD which kernel modules to load.
Yeah, so that you can
for you. Yeah.
So yeah, you can mark a container with like a list of kernel modules it needs, and at startup time, LXD will make sure that all of those are loaded before the container starts. So other interesting things you can do with pass-through is, and it's somewhat recent, is all the stuff we showed so far is on server and it's all nice and fun, but you can also run it on your laptop and maybe you want to run, say, some graphical application inside the container. We've got support for that as well. It is somewhat interesting to get done sometimes. So I've got a container called Heaven, which currently has, actually wanted the entire config, not just the devices. Currently, nothing really interesting set on that container. If I go in that container, there's the Unigen Heaven benchmark, which will not run because it's a container. It doesn't have access to my X server. It doesn't have access to my GPU or any of that stuff, because why would it? But we can fix that. The first one is going to be a pretty long one. It sets up a proxy device, which can connect on 2 different network namespaces. In this case, your laptops and the container. And in this case, we'll forward the abstract Unix socket that's used by X11 from outside. Oh, yeah. Yeah, you're assuming that that's working with the craziness we've got from there. OK, so nice at the top. It will forward the abstract Unix socket of X11 from inside the container to the outside of the container. And also, it uses the right UID and GID so that you don't need to mess with X authentication. In this case, it just uses my current UID and GID. And because they're weird, I'm shelling out to ID, because I don't even know what they are. So we had that device, at which point you, in theory, have X11 access, but it's still not quite useful for a GL benchmark. So it's better to also pass GPUs. So just pass all GPUs. Then you want to set the environment variable for X11. And because it's a container, you don't want to rely on X shared memory. So you've got an extra environment variable for Qt telling it, don't do shared memory. That gets you this as the final config, which effectively has a bunch more config keys and the GPU device and the X7 proxy. Now, if I go in there and I go root Heaven and I run Heaven, it's not complaining anymore, which is great. It's actually showing me this. And we can hit run. And this is a Intel graphics card, so don't expect it to be super impressive. But I mean, it's impressive enough that it runs 30-ish FPS or something. Yes?
Why isn't X11 complaining about not having the correct MI2 cookie? Like, why didn't you have the right X host?
So that's the trick. If you use the abstract Unix socket and you map the UID to be the UID of your user, then it just pulls the ucred and lets you access it. So that means I don't need to have the X authority file in there or do X host plus, which is the other trick that other people do, which is not a good idea in general.
Yeah,
Yes?
you don't want a keylogger.
Yeah. And also in this case, my laptop is actually running Wayland with X Wayland on top, but that's still working. So let's close this stuff. Yeah, good. All right, and there. All right, so that was X11 stuff. Now, 3 more demos. We'll see. All right. Another thing we can do with recent LXD is actually, because we run system containers that don't require modifications effectively, we can get into a normal system. In this case, it's a CentOS 7 system that's running, I think, just Apache. Yeah. And we've got a tool that's called LXD physical to container that you give access to you give the IP of a LXD instance. You give the name of the container you want to create, and you give where the file system is. In this case, we're going to move itself, so just slash. You enter your creds for, oops, I forgot to delete it, sorry. There we go. OK. So if we run that, it's going to transfer that system using the internal migration API that LXD has for container for host-to-host communication, and that's done. At which point, I do have a C1 container on my LXD host. I can start it, and we've got it's still starting. It's going to start. There we go. HTTPD is running. So we can move physical systems or virtual machines into containers using a tool like that pretty easily. Or any root file system you happen to have around, because you can pass that instead of slash. And that lets you move that stuff very easily. And let's see if I can do clustering in 3 minutes. That's what we're looking at timing-wise. So I've got 2 more machines. I'm not sure what's their state, because I had some difficulties earlier. Did I run that? Because those Ubuntu server comes with LXD pre-installed, but it comes with the LXD LTS release, not with the latest thing. And for demos, it's way cooler to run the latest thing. So we've got a tool that lets you move any data you've got from the deb over to the snap package, which is what I'm running now because I forgot to do it earlier. OK, so that one's clean. So let's do that one first. I'm going to need to know its IP address. OK, it's 1650. All right. And I run LXD init. And this time I say yes to I want clustering. That's its name. 1650 is good. Are you joining an existing cluster? No, we're not. It's a new one. Choose a password for other nodes to join. And then the same questions as we saw before with what storage backend do you want, what network, and all that stuff. So I'm just going to hit enter a bunch of times. And yeah, you got a cluster. So right now, it's just normal LXD. But on the second node, I can do LXD init. Yes to clustering. Choose the default name. Default IP is fine. Joining a cluster, yes, we are. Where is the cluster? So you enter the IP of any existing node. You can go and compare the fingerprint or just believe that it's right. Enter the password for that and say yes to losing any data you might have on that node, because that's what's going to happen. And if you wanted to override some node-specific options, like right now we just used a loop device for storage, but that might, if you were to use a block device, the actual path might differ between nodes. So it's asking you if you want to override any of those to another path, because the path might differ. Anyway, that's done. So right now, there's still no containers, so it's kind of boring. If we do cluster list, we see 2 nodes in the cluster. And let's just create the smallest possible container, which is Alpine image. OK, that's running. And we see it's running on Utero, which is the other node, actually. And if we run a second one, it will most likely be running on Edvu. Yep. So it does, if you don't tell it where you want things, and you can tell it with -- target, it will just pick whichever is the least amount of stuff. Most trivial load balancing you can think of, but it works. And it sets up a very minimal overlay type network. Oops, that's true. I always forget that Alpine doesn't have bash. So you can actually ping between the 2, even though they're on different nodes. That's just set up for you, and that kind of works. And I'm going to be running over by a minute, but whatever. As we said, LXD's got a remote API. That's what it uses internally for those commands. It also means that you can, like on my laptop, which is what we are at right now, I'll probably have once Stephane this remote out here. So you can add a remote. We'll call it cluster, and we'll enter one of the IPs of that cluster. Yes to the fingerprint, same password thing. OK, so that's added. And now I can do list what's on cluster. And from my laptop, it's listing what I've got on those 2 machines. You can switch your default remote so that if you never actually interact with LXD locally, you can just set your remote machine as always being what you want to talk to. It also means we can do things like that. So we can let's stop C2. Yep, and let's move it. So I want C2, and I hope I don't have a C2 locally. We shall see. And hopefully that's going to work. I mean, the cluster is on the other side of the country, so my laptop is here. So, oh, that worked. Pretty my VPN works, and we start the container, and now that container is running on my laptop and not on the cluster anymore. So that's how you would manage multiple. You can do it with multiple clusters, like kind of a production and staging clusters, and move things in between. Or you can do that with like your laptop and desktop machine, or whatever you want really. So that's using the LXD API to move things around. And that's it for the demo. We're gonna move back to this thing. And I'm just gonna go quickly through a few other things. As we said, we've got images. That was one of the questions from earlier. We've got images for all those distros right now. Adding more, not super difficult, but that's what we've got. We publish them daily. Images auto-update in your local image server. So if something was cached and has been used within the past 10 days, the newer versions will be downloaded. And they effectively expire out of your local cache after 10 days since last use. LXD itself is available on all of those in some different ways. Alpine Linux got native packaging. Arch Linux, you've got an AUR, or you can use the snapd AUR and then install the LXD snap that we publish. Debian, you need to install snapd and then install the LXD snap. Elementary, you need to install snapd and use the LXD snap. Fedora, you've got a Copper repository that someone maintains with it, or you can use snapd and the LXD snap. Gentoo has got a native package. OpenSUSE's got snapd and installed the LXD snap. Manjaro is the same as Arch Linux, so it's AUR or snapd plus LXD snap. Solus is snapd plus LXD snap. And Ubuntu is either native, which gets you the LTS release, or you use the LXD snap to get whatever's more recent. You've heard me say LXD snap a lot of times. That's kind of what we prefer as far as the upstream, because everyone runs the exact same bit, whatever the distro. So we need to care about different kernel releases, but we don't really need to care about what version of the LVM tools you've got or that kind of stuff. It's much easier for us to support and replicate any issue you run into. But that being said, we do support running on a wide variety of versions of different things. Like we've got version detection for LVM, version detection for DNS mask, version detection for rsync, so that we can use the right features depending on whatever the hell they support on that particular platform on that particular day. That's back to you.
Yeah, so LXD itself, as I said before, I think it's two-part. There's LXD, which is a shared library running the containers, LXD, and which is written in C, but LXD itself is written in Go. If you do any kind of web interaction, it's usually pretty useful, barring a few more corner cases. It's fully translatable. We have some translations for, I don't know, German, French, Japanese, Korean.
Yeah, Russian, Korean, some stuff. Yeah.
Exactly. We have various API clients. There is one in Go, obviously. Someone maintains a Python API, right? And there's also a Haskell API. I don't know, but we have a Haskell API. And it's Apache 2 licensed, and there is no CLA whatsoever. With all our projects in the Linux containers namespace, we require signed-off by lines, which is this general kernel coding style. So if you make a contribution, we expect you to do signed off by your name and an email address, and that's it. No other legal bullshit involved. Cursed again, sorry. And this is the repo where LXD itself is developed. And you should look under the namespace, the LXC namespace itself. There's a bunch of other interesting stuff out there, also for other container runtimes like LXCFS, and there's also LXC and a bunch of other stuff. So just a quick recap.
There was a question around.
Go on.
Yeah, I was curious. What are the limitations of this environment? Like, what can't you do with this environment?
What can't you do with this environment?
Yeah, like when would I go to LXD, or when would I go to VM, or when would I go to a plain container? How do I make that decision? Is there any limitation in this environment?
So our idea is, ideally, if I were a marketing person, I would say we try to be a full replacement for virtual machines. But obviously, there are a few cases where probably virtual machines would make more sense, I guess, if you care about real hardware separation, probably.
Yeah, so I mean, the kind of go-to answer we have for that is that when you are in a case where you're running a Linux VM on top of a Linux host, and even worse if they're running the same kernel, it might not make quite that much sense, and you might be able to get significantly better density with containers. The main thing is that idling containers, they don't use any resources. They won't trigger interrupts. You won't have to like context switch to the VM to deal with some network interrupts or that kind of stuff. So you can run thousands of idle containers, whereas you might be able to run hundreds of VMs. It does depend. Obviously, other operating systems you need to be using virtualization for that. There's no magic there. If you need to load weird kernel modules, you need to do that. But in a lot of other cases, when you're just like we've got people that are just doing Ubuntu on Ubuntu or Fedora on Fedora. And they might want a slightly different version of the user space, but they don't really care what kernel they're running. There's really no good reason then at that point to use virtual machines.
I mean, even for the kernel case, the kernel is pretty good at being backwards compatible. And we once did a crazy demo that was super fun where we ran like Debian, I don't know, 2, 3 or something, like one of the first Debian releases on a 4.14 kernel or something.
Also, actually, I can show you something because I've got that here. So. Start CentOS 3. Oops, that shows some of the Red Hat release. Oh, it predates Red Hat release, sorry. What was... Oh, that's a good point. Nope, none of that either. It's old, seriously old.
Yeah, the thing is, for example, the user space assumes, or PS has a fixed buffer size it expects.
But, it still tries and get updates, so there's that.
Yeah, it expects a buffer of maximum of like 1,024 bytes or something, or even smaller, and obviously the proc, like various files on the proc have grown over time, so it just...
Yeah, so it just takes a little bit, because we've got a hack to fix those tools, and it applies at boot time, but wasn't early enough, so now PS actually does work. Yeah, it does have there was some expectation from CentOS 3 that like some particular files would fit in 64K or whatever, and it's not the case anymore on any modern kernel, but it's easy enough with the right fuse driver to just trunk, like it was like meminfo. CentOS 3 is not gonna care about any new field in meminfo, so you can truncate like half the file away and things are fine. But otherwise, the user space works fine. I think we tried running the what did we try? We tried running Slackware 1, and we started running into issues there.
Well, the only issue was basically that the kernel doesn't run non-ELF binaries.
Yeah,
but we probably even could get that to
we
work.
Were running we were trying to run a distro that predated ELF, being the binary format, which we managed to get working, but needed a 32-bit kernel with the right option enabled. Then that would actually work, but not on my x86 64-bit laptop.
But yeah, so even in the case where you care about just about the user space, you can run it on a wide variety of kernels. If you need a different kernel, then yes, you will need virtual machines. Exactly. As I said, is safe by default, which means unprivileged containers. So we use user namespaces and isolate the privileges that you have inside of the container from privileges that you have outside of the container associated with your UIDs and GIDs. We try to provide similar resource control to virtual machines, which you've seen with memory isolation and CPUs and so on. And we support device pass-through, so all of the stuff you've seen before, you can pass in a KVM device, whatever. And it's extremely low overhead, so typically identical to bare metal. That's the whole selling point of any container, essentially. And low-level access to any devices supported by Linux. There is no special stuff. You probably need a kernel driver, the kernel driver, but that's about it. And it's a simple REST API, as you've seen, that you can talk to it with curl if you wanted to. If you're bored, you just could write a shell script that does all of this for you. And clustering support, as Stephane mentioned, and it's production ready. So I mean, it's tested in the wild. Stephane?
Yeah, I'm just getting the next step set up. Yeah. There we go. Okay. Cool. So we kind of did questions out of band. That's fine. We're not gonna go to the part where you can actually do stuff yourself. So if you've got any questions during the lab, we'll answer those. That's probably going to be easier than making a break for questions right now. What you can do there is go to that URL on your laptop, and it's going to be getting a Google Doc with instructions on how to get things going. The way we've done that is we've got a bunch of cloud instances that you guys can use for that. So even if your laptop is running on Windows or whatever, it's not a problem. So long as you've got an SSH client, you can follow along and use those cloud instances. The way we've done it is there's a spreadsheet with the IP addresses. Please mark down your name next to it so that people know that you claimed that one and you don't end up with 2 people trying to use the same one. That's about it. We're trying to get Google to allocate more IPs. We've kind of hit a quota, and we're still waiting for them to clear that. So we were trying to get 2 cloud instances per people. And given that some of you left the room now, I think we're good even with as many as we've got right now. So go through that. Christian and I will be walking around. If you've got any question, you get stuck on anything, you've got any other questions, just ask us. We're there for that. And have fun.